Okay, well, let's get going then. So we are very lucky to have Carl Tape here as our colloquium speaker today. And Carl is an associate professor of seismology at the University of Alaska in Fairbanks. And Carl did his PhD at Caltech and then an NSF postdoc fellowship at Harvard, and he moved to Fairbanks in 2010. So Carl, as you can probably tell from his PowerPoint, is an expert in seismic tomography and seismic wave propagation. And much of his early work, I think, was dedicated to imaging the crustal structure in Southern California. But since he's moved to Alaska, his more recent work has seemed to be immersed in tackling some of the very unique challenges of doing seismology in Alaska. So he's written papers about what happens when a bear tries to eat your seismic station, and how do the northern lights affect the seismic record, and also what the effects of seismic noise from the exciting Alaskan weather are. And so having dealt with all of these surface issues, Carl's now going to tell us about the subsurface of Alaska. And the title of his talk is Earthquakes and Earth Structure in the EarthScope Era. So thank you very much, Carl.
Thank you, everyone, for joining. I'm really impressed to see so many people on this call. I forgot one word in the title, which was Alaska. So if you're expecting the entire country or just, this will be focused on Alaska. All right, let's get into this. I show this photo to try to convey sometimes what is Alaska about? And for me, this photo takes a lot of things into account, but this is a shot from a student on the road. And, it just, if you kind of imagine, what are the situations you have where someone can freely just shoot at signs on the main highway? And that's kind of the remoteness that Alaska speaks to, which ties into why it's so challenging to do scientific work up here. And in this case, the word missing there is Minto, a native village west of Fairbanks, and Manly. Both of these feature in my talk, and they're both. One of them is an EarthScope station, TA. The other one is an EarthScope quality, an upgraded station at Manly. Here's my outline. I'll go over some introductory material. I'll mention regional moment tensors, getting at this style of faulting in Alaska. Some highlights of earthquakes. Some of them you'll be familiar with, but I'm assuming hopefully not all of them. I'll finish with not much on seismic imaging, just to say there's a lot of work just starting. And the theme here is really that improved station coverage and quality enable new discoveries about earthquakes and earth structure in Alaska. I'll start at this level. It's a departmental colloquium. We're all on the same page with plate tectonics. I am coming from right here in the center, up on the North America plate. We've got Pacific subducting along the southern margin and a strike slip, kind of like the northern San Andreas fault along the eastern margin, the Fairweather fault. If you look at Peter Bird's global plate model, you'll notice this hatching pattern in a lot of places where plate tectonics doesn't function as simply as all the activity is right on plate boundaries. And you can see in Alaska, there's the whole thing is just a big hatch zone saying, good luck doing plate tectonics up here because there's a lot of complexity. Similarly, the Himalayan region, there are large chunks of the world where we have challenges, and really it's exciting places where deformation is complicated, earthquakes are everywhere. Here's a figure from a paper on faults of Alaska showing the convergence between the Pacific and North America plate split out in this bar. So it's like 5 centimeters per year, and most of it's down here in this collision zone, actually. But then, there's other millimeters per year that is somehow accounted for, lots of question marks in here. But this is another picture saying that the convergence between these two plates is spread out over a wide range, and that's what makes the earthquake and EarthScope different in Alaska from other parts of the lower 48. It's that there's a lot of local events that are going to be captured by these new stations. This is going to be a review for many people, but this is just showing as a function of year what the EarthScope seismic array was. It started in the West Coast, and they were picked up and kind of rolled over by the time it reached out here in 2015. And at that point, it started going to Alaska. So this is a monumental NSF achievement, just a reminder that of sort of what it was. The Alaska component came at the end. So in the lower 48, this was the style of installations. There were trucks driving, there were, ditch diggers, vaults being buried. And so it's very different. So in Alaska, step one, like how do we, move a drill or transport one in a helicopter to a remote site and drill into the rock? So totally different logistical, and hopefully you get some appreciation for the difference between those two photos in terms of the challenges. But I'd also argue that the challenges are worth it, given that there's a lot more activity and a lot more to discover in some sense in parts of Alaska where there had never been the capability to get seismic data or geophysical data. So here's a picture of what these stations look like in Alaska. We were mentioning in the discussion sort of when you have an opportunity to make a measurement, make a lot of measurements. So there's soil temperature for permafrost, infrasound for volcanic eruptions, seismometer in the borehole. There's a weather station. And so all of these are this is what the standard sensor looks like here. And you get some idea. Note there's, here there's no trees. So above certain latitude, there's no trees anywhere. And you can imagine these would stand out on the tundra. So this is a picture showing seismic noise. For the seismologist, I think what's key is that when we do seismology, there's a background level of noise that we may not want to deal with. And so it sort of guides us it gives a measure for the quality of a station. So this is showing the horizontal noise level, and then on the vertical component shown in the solid lines. And I'm comparing one of my stations that I deployed on a Pascal project with a really good regional station that's AKMLY. But it's this information that tells us what kind of science can be done over which frequencies. So a lot of the scientific processes we're looking at, they happen within a certain frequency range, and we have to be aware of that, because if we can get better quality stations, we can do different kinds of science, and you'll see some examples at the end. This is what that MLY station looks like, just a rocky knob with a bunch of continuous GPS. This has a couple other instruments as well, but this is what a station looks like in Alaska. Probably one that could take a little bit of wind without anything to buffer it. This is Kyle Smith. A lot of the work I'll show, he graduated last year. This is a post-hole seismometer. And just to advertise one of his papers, it was really amazing to see, just from looking at noise, what kinds of influences were active in these remote areas. So they're remote, away from people and cultural noise, but there's still, you could see rivers, wind, amplification from sedimentary basins. So it's pretty interesting as an environmental tool. Even though we were out there to capture earthquakes, it was capturing all kinds of stuff going on. This shows what one of the sites looked like off Spur Volcano. So you have to imagine, for the EarthScope array, drilling a borehole for the seismometer, getting this thing in a helicopter out here. And so the real question is, why so much effort for data quality? And I'll hopefully try to convey to you the advantages of getting this kind of enhanced data quality by putting the seismometer deeper in the ground than I would be able to with conventional means on a temporary project. But this photo kind of captures, you've got this drill rig on the side. This is Spur Volcano in an extremely remote part of Alaska. Let's go put a seismometer in the ground. Here's another one. This was the reference site for a paper that Kyle led on looking at seismic basin amplification, and just again kind of conveying the setting for what one of these sites is. It's clearly bedrock. The seismometer is in a hole drilled in bedrock, and it seems to be pretty far removed from at least cultural noise. Here's a picture of Alaska looking down. I'm coming right here. Maryland, we're on the same plate, at least. Doesn't seem so far in this picture, but This shows the outline of the plates as shown from earthquakes, and it's kind of an interesting perspective to look at the North American plate. Here's 1 year during this EarthScope era of seismic stations, 2018 in Alaska, and there'll be a lot of geography probably for some of you on Alaska. 55,000 earthquakes in this year. There's a magnitude 7.9 offshore, magnitude 7.1 near Anchorage, which that title slide was from, magnitude 6.4 and 6.1 up here. I can't say it in any other way, but it's kind of a good year for earthquakes in Alaska. A lot of activity in that there were a lot of stations around Alaska to record all this information. But this gives you some idea in a given year what kind of deformation and activity is ongoing. This shows the 2019, the following year, a lot of aftershocks left over from some of these big events, 7,000 events in this Purcell Mountain swarm. But just again, these events have all been captured with quite impressive data quality and coverage across the state, and we'll see some of that. So what do I mean by the EarthScope era? This shows a map. You can create this from an online IRIS GMAP tool, see what stations were live on what date. So this shows October 1st, 2014. This is a very large region. Like this is, California would be about this size right here on the western part of the state. So you see the coverage and what is not covered, I guess. 1 year later, 2015, 2016, 2017, fully deployed across the state in regions that have no roads. So there's one road that goes from from Fairbanks up to the oil field, and that's it. So there's no roads out here, which gives you some idea of what the logistics were involved. And this is a couple weeks ago. EarthScope era is still alive, I'll say, is that these stations are live and active now, and kind of remains to be seen what the future is. But at the moment, it's an impressive geophysical acquisition going on right now. So I'll go into something about regional earthquakes, and this is looking at during this era, what can we gain by having this kind of station coverage? And this is looking at some of Kyle's work, a catalog of mechanisms of earthquakes from 33 events, very high quality studied, where we were particularly interested in how the wave field from these events influenced a local structure, sedimentary basin in central Alaska. But this shows the events and the kind of activity that includes some magnitude 7.9, 7.1 during this era. And just to give an idea, I'm just showing one example of a kind of intriguing event where there's thousands of events going on in this region that we don't know very much about. The sources, what is shown here is that Kyle tries to find the best mechanism for each depth. So you grid search over different depths, and for each depth, you search over magnitude and mechanism to try to see what fits the seismic waveforms the best. And this shows we can consider a fault plane solution, or we can consider a full moment tensor where, for example, for nuclear explosions or volcanic events, you might want to allow for something more complicated than simple slip on a fault plane. But anyway, these events are challenging, these particular ones. They seem to be very shallow, and maybe as we study this swarm of thousands of earthquakes, we'll get some idea of what's going on so far away from the plate boundary in northwestern Alaska. 7,000 events need some sort of explanation, in my view. And the nice thing about working with this data set is you don't have to wonder so much about data quality. So this shows the coverage, the stations being used. And if you see there's sort of a letter, number, letter, that's the signature of an EarthScope station. So for this region, if you ask the question, remove all these EarthScope stations and then study this event, it'd be a very different story. We would be wondering, like, do I have the right fault plane? The uncertainties would be much higher. So we all, in whatever we're doing, data quality is always something that can at least reduce uncertainties. I mean, and sometimes having more data makes it harder because you find that you can't explain even with the good data, which is kind of in this case, an example where on the left, this is showing you what we kind of do for these, to get these mechanisms, we have body waves that are recorded in black here, and then surface waves recorded in black, and the red ones would be the synthetic seismograms that we've found by using this best fitting mechanism. And this just shows the closest 4 stations. Of course, you can't see what's on the left, but that shows the PDF that goes with this event, showing 84 stations, just really spectacular coverage. And yet for these events, there's something more to the story. You can't get perfect. If you have tremendous coverage and you still can't fit things, then you have to start wondering about other interesting things like the structure or the source model you have. So I'm going to go into highlights of earthquakes that have occurred during this era, sort of 2017 when things were fully deployed, but also starting earlier in some parts of the state. And these are the selections I'll choose. So up north, very far from the plate boundary, northern Alaska, Kaktovik, the Prudhoe Bay oil field is up in this region. When you hear about Arctic National Wildlife Refuge, that's what this is. It's the northeastern part of the state. And so here's these events were the largest northern Alaska earthquake since 1958, magnitude 7.3 Housley event. And in fact, above 65 degrees latitude, there's only been one other earthquake ever recorded. So generally on the high Arctic, there aren't a lot of earthquakes just based on what plates are up there. But in this picture, the authors inferred sort of bookshelf style faulting in this left lateral shear zone with right lateral subfaulting. And what was really cool to me was that there was good enough INSAR view of the ground displacement to really lock in where the faulting occurred. So in a place like Alaska, where there's a lot of coverage by ice, and we generally don't get surface ruptures that are usable like this. I'll look in at a couple. This is a map showing magnitude greater than 7 events, 1899 to 2020. We're looking at some of these earthquakes were large, like 1964, magnitude 9, Denali Fault, magnitude 7.9. But I think, when you look at in a couple year era where EarthScope stations were out there, we actually had, this is the Anchorage, this is 7.1 slab event, and this is the offshore Kodiak. So it's actually a fair number for a 5-year period to have this kind of recording. So we'll look at these. This is just one figure for that Kodiak earthquake. Hopefully, even if you're not a seismologist, I think this is a kind of event that is pretty inspiring to see that this kind of really complicated rupture, I mean, multiple faults in the oceanic crust, just the dots of the aftershocks showing this kind of, it looks like a hatchet almost. And what's fascinating is if you look at where this first style of faulting came really to the forefront was in offshore Sumatra. And I rotated the author's figure to show this pattern. I'm just kind of struck by how similar these two patterns are. One of them, this is a magnitude 8.6, but this idea that this event, very complex faulting of this is not a world where there's just one fault plane breaking. There's multiple faults breaking and trying to tease out the timing. As a side note, the EarthScope stations are unfortunately just like too far away to be extremely helpful here. If this had happened in mainland Alaska, or if it does, you'd have a different story about understanding this complexity. But nevertheless, seismologists put together an interesting picture on this. We'll look at this Inniskin earthquake, 7.1, deep in the slab here. And this is the Anchorage region. This is Cook Inlet Basin. So I'll have a couple slides on this. This earthquake, even though it was 120 kilometers down, the shaking on the Kenai Peninsula was pretty strong, damaged the roads. It ruptured a gas pipeline and destroyed a few homes in there. So despite being a fair distance away from this spot and also 120 kilometers down, you still have ground shaking that can be damaging. I'll also add that for that event, I had a lot of stations out in this basin that amplifies ground motion, and all the red ones are stations where the data were clipped. So meaning that they're not designed to handle really strong ground motion. And for a 7.1 earthquake, even and a deep deep version, all these stations had problems. And so that's something that lends us to think, well, what other, what other instruments could be used? One of them that was interesting was by Ronnie Grappington. He used GPS. So GPS can record the ground motion and stays on scale, and was able to get recordings of how the basin moved in a place where all my seismic stations that were out here, none of them were on scale. They all had problems to record this. So this is an interesting study out of that earthquake. I had this figure on my front slide. It's one of my favorite just snapshots to remind people how complicated the wave field can be. This is a computer simulation. And so this is kind of one of the main things in my research that I do, is try to characterize as best as possible the Earth structure, and then use the best available source model and see what the seismic wave field looks like. And this shows a snapshot in time from a computer simulation where there's been a lot of the wave fields kind of dragging and being left behind in this very slow sedimentary basin. This is actually where we know a lot about this basin, because it's where oil and gas is. So gas was discovered in 1957 right in this area. So lo and behold, we have good information on the structure here. And so I'll show, hopefully this will play, I'll show the movie that snapshot was grabbed from. You can pay attention to the timing. So you'll see a P wave, and then you'll see an S wave, and behind the S wave, you'll see a lot of the surface wave and amplification in the basin. So it takes half a minute in, because it's got to come from 120 kilometers. And you can see this wave field kind of wrap behind as it passes through. And here's Anchorage. So you can imagine that the shaking is expected to be quite strong on the western Kenai Peninsula, which is on top of this sedimentary basin. This gap is Cook Inlet. So this is a shallow ocean coming in here. And so you see after time, there's still a lot of ringing effect going on there. I just showed this, a screenshot I once saw in the New York Times after the Mexico City earthquake. I was so happy to see an actual computer simulation on the front page of the New York Times, but they were trying to use the simulation to explain how the ground shaking could be stronger based on Mexico City being built on this ancient lake bed. But part of the point is that it's not easy to see. You can't record a picture of this wave field unless you have thousands of sensors, and even then, you can't connect necessarily all the dots or get the kind of motion that you can get from these sort of simulations. So it's a good use, and it's relevant for thinking about seismic hazard. As a side, we were interested, Kyle and I looked at Cook Inlet Basin and how the ground motion was amplified by this basin. I like to point out here, when you do some vertical exaggeration, you get some appreciation. Redoubt Volcano is a spectacular looking volcano, and it looks really big. But when you put it next to the depth of the basin, you realize how much sediment is down there and what kind of impact that might have on ground motion. So when compared next to the volcanoes or these Kenai Mountains, really spectacular mountains in Alaska, the basin kind of dwarfs both of them. So on to the 2018 Anchorage earthquake. There was a special section in SRL that our Cook Inlet study was in, but just showing some of the work on the left here, and I'll show some sections from that. This is showing, this is Anchorage right here. The subducting slab is beneath Anchorage by sort of tens of kilometers. These are showing aftershocks of the magnitude 7.1 earthquake. They all look like pretty similar, normal faulting, similar to the main shock here. And you see some cross sections through A, B, and C, looking at the aftershocks. Here's A, B, and C, and trying to tease out, what are did the aftershocks break which of the planes, which of these two fault planes was the one that the earthquake hosted. And I really am inspired by this, because here we have good data coverage. We're on top of the event. There's INSAR, and we're still challenged to figure out which of these two planes was the one that hosted the earthquake. And I think that, just fundamental information is still a challenge in seismology. And I don't know if that question has been adequately answered. I mean, you could argue, well, maybe both planes ruptured or maybe the aftershocks are on a different plane, but it's not unequivocal which plane down in the earth in this slab broke in a 7.1 earthquake that caused widespread damage. Schools were closed. There was a lot of damage due to something. And as Mike West, the state seismologist, said, this is actually far away. It was down deep in the earth, 40 kilometers down. It wasn't like this was in Anchorage. So, and in spite of that, there's a lot of damage. So we need to understand, especially where we have the data coverage, this basic information. This is just showing a follow-up on that, trying to figure out, from this cloud of aftershocks, you have sedimentary basin in here. Some there are sensors around, but it's a challenge to, reliably get these earthquake locations and try to figure out what the story was. I wanted to show this. It's a student at UAF working on landslides. There were 2 landslides off Iliamna volcano in 2016 and 19. And what you see here is they were very similar. And so you have this repeating experiment for you, basically, with seismometers and, in his case, infrasound to look at this avalanche. You can see right here in this photograph from Homer. And what is shown here are waveform fits between the recording in black and the modeled seismogram in red. And this is long period. So this is at 15 to 80 seconds locally, where you see this landslide signal. And these are spectacular fits for this event. And I think what it's a testament to is really that we're on this is showing the signal versus the noise. But when you have low noise levels out here, you can study things like landslides, and even in some cases, the horizontal components, where you generally have higher noise levels, and it's much harder to see what the signals are. So just another example of where this data quality can lead to kinds of things that are somewhat unusual in Alaska and not found everywhere. I wanted to show one of our studies looking at another sort of long period signal. This is in the center of Alaska on a fault zone. There's a very small event, something like 3.8, near previously in 1995, a magnitude 6 had occurred on this fault. And so this one is occurring down 20 to 24 kilometers in the crust, which is here something like 30 kilometers. So deep down in the crust on this fault system, which is predominantly a strike slip fault system with left lateral faulting, you have some exotic events, and this is one of them. And so this shows for one of these TA style stations, here's the noise level, and here's the signal for the station between 20 and 50 seconds. This level is just barely above the noise level. So if you have a noisier station, you don't see this signal. So that's why data quality matters. And what you have here, and this is showing you, the waveform fits. Red is the model, black is the data. It's pretty much as good as we've ever had. I mean, this is a special kind of earthquake that was deficient in high frequencies. But what you see here is the waveform fits and the coverage. A lot of these were the ones that were usable were the EarthScope stations shown here. So that allows us to get a reliable mechanism and see something more about these. So in this case, what was interesting about it was that the source time function for this magnitude 3.8 was something like 10 seconds long, when normally it'd be a half second. So there's something special going on deep in the strike slip fault system that is generating this kind of event. I'm going to finish with some overview of some seismic imaging results from Alaska that have come out recently. And so this is kind of on the end of 2017, and even slightly before that, when the EarthScope stations had been deployed. All of a sudden there were data that were available that hadn't been used to look at the northern and western part of Alaska. So the other parts of Alaska, there had been data, But I will say what's interesting about being last on the EarthScope transition from the lower 48 to Alaska is that people had tested and refined their techniques so well that by the time EarthScope stations came out, you know, it's like people were ready to go. And that's reflected by just the number of papers that have come out in the last couple of years. So this is showing at 210 kilometers and 270 kilometers, an example from the deeper structure in Alaska. This outline is this over-thickened Yakutat slab. It's basically an oceanic plateau that's colliding and subducting, forming some of the highest coastal mountains in the world are right here due to this kind of collision. And what you see, these are from in the last couple of years, a lot of emphasis on the crust, the crustal structure of Alaska through different techniques. And I'm just showing you, this is an example from Elizabeth Berg's study, looking at 1 kilometer, 25 kilometers, looking at a lot of heterogeneity, sedimentary basins, things that I get excited about. When I see this map, it's you know, it's like, well, here's a Cook Inlet Basin, Yukon Flats Basin, Copper River Basin. This is the North Slope. When we say North Slope, it's a gradual slope to the ocean where all the oil and gas activity is. So this is kind of the realm where we are in. And I would say that from my standpoint, what's coming within our group is that we're going to use, so this is a map showing the magnitude 3 and greater earthquakes, which are, you know, sources of information for seismic imaging. This shows 3 smaller kind of focused regions for wave field simulations, where we would take the best available models and start with those structures, expose them to, you know, different kinds of earthquakes, run simulations, and then try to improve these tomographic models using simulations through this adjoint tomography method that is becoming more widely used. So the way I see it is that we've gone through quite a bit of effort to, you know, establish reliable regional source models. I've collected data on a couple different projects in sedimentary basins where I feel like, you know, the need to understand the wave field in those settings kind of warranted the deployment of seismic stations, such as in this region and in this region. And so that's where we're headed right now, is to sort of build on these recent results and try to improve them. So yeah, the last point is just to come back to the beginning with these, in this new era in EarthScope, with both the station coverage and improved quality enable new discoveries. And we're just starting on this. So final slide is to say, check out, there's we had a museum exhibit on a century of earthquakes in interior Alaska. And a lot of that was fortunately translated into a virtual exhibit. And so if you're kind of interested in exploring history and earthquakes in central Alaska, I encourage you to just check this out. You can Google Shake Alaska Museum, and I'm sure you'll find it. So thank you very much.
Hooray, thank you very much, Carl, for a really, really interesting talk.
Normally, I am always, this is the first time I've given this full talk, but I see I'm at 30 minutes, which is probably better than rushing through a talk at 45 minutes, but I do have time.
No problem. I'm sure there's going to be questions. I can see Ved's unmuted himself. Why don't you go, Ved?
I did it quickly, and then I was like, wait, no, I'm supposed to raise my hand. Thank you very much, Carl, for that. I have so many questions about different parts of what you were saying, but I'm going to hold off till the end because I want to like monopolize your time. So I'll let other people ask questions after and then I'll take over.
Okay, the pressure's on, everyone.
Well, the next question is Mong Han, and I'm guessing Mong Han has 2 questions because he normally does. Is that right?
I kind of have 3, but I will reduce to 1. But before I ask my question, I just want to say I learned how to read Hudson plot from reading tape and tape.
Oh, you learned to
read a Hudson plot.
Okay.
Even though it was not about that, but it's how I learned how to read it. So.
Well, yeah, that study, yeah, it's sort of a lesson. We gently were suggesting in the study that maybe you shouldn't be using those plots at all, but I don't think we were very direct the way we wrote the paper. But anyway, there's different
but
ways.
it's how I learned how to read that in any way. And
Okay.
I do like your approach. Okay, so I guess my question is, you show the VLFEs where that's, somewhere in the middle of the continent. So I'm curious, A, is what kind, if there any kind of unique environment that allow the VLFEs to happen there, and also, in the subduction interface, we commonly see those slow slip events or tremors. So do you see that in Alaska as well?
So there's a lot of studies on slow slip events in Alaska, but what's interesting is like every subduction zone seems to have its own signature, and in Alaska they tend to last several years. You need long time series, and they're happening somewhere on the plate interface at sort of in the like 70 to 90 and even 100 kilometers depth. So whenever I see these figures, I'm thinking, what is going on between, it means the upper plate is mantle, okay? So it's mantle against downgoing slab, and that's always intrigued me. So there are slow slip events, but I don't believe VLFEs have been detected in that realm, such as in Japan. So back to the question about the interior, I don't have any answer other than to say that the existence of so many so there's a sedimentary basin that's about 5 or 6 kilometers deep on top. There's this transtensional setting of a step over with the basin in between. And on these fault systems, there's deep earthquakes. And I mean, we know the depths probably within a kilometer, like they're at 20, 22, 24 kilometers deep, and we have earthquakes right at the bottom. And so we've seen, I think, only 2, maybe 3 examples of this. And I don't know what to say. I feel like my job as a seismologist is to characterize it as best I can. But you are right to say what is it about this area? I mean, I don't think people have found these in Parkfield, for example, or other studied systems. There was an abstract I remember seeing at one point, but I don't know why. All I can say is it's got the signatures. It's got a 10-second source time function. Chen Ji from Santa Barbara actually did a finite source inversion with these waveforms, and you see, what is it that's a magnitude 3.8 earthquake? You can see the waveforms at 1,000 kilometers away for an event that size, because it's got this big long period signal. So I hope you're interested, but I don't know what's going on deep in the crust.
Thanks, Mohan. Next up, we have a question from Laurent.
Hey, Carl. Thanks. Very interesting talk and evidently amazing data. I am curious about all of those structures that you showed in the various maps of the interior of Alaska, all these parallel structures coming from Denali, but going all the way to that town, Captoveco, whatever. I mean, so you had all of those parallel structures making those stuff. In one of your last slides about the crustal tomography, we could see some of those maybe all the way to 45 kilometers, which I'm not sure if you're still in the crust or in the mantle there. But the question really is, how deep do they go, and do they go into the mantle? Have we found any correlation with the slip rate on those structures, their age, or anything like this? Have we learned much about their down deep continuation through the studies through the data you're able to collect?
So you're referring to there's both the tomographic structures and then fault structures. So are you referring to maybe like 45 kilometers? What's going on here? Or?
Well, at 45 kilometers, there were some variations in the velocity that seemed to really be, in some cases.
Sorry, I thought I was sharing, but I was not sharing.
Right. So in those, for example, at 45 kilometers, we can see the Denali faults kind of limiting between the red and the yellow one. Yeah. But even like there's one very much more north, about like 65 or 6, that seems to also be a boundary in here. 25, we see similar boundaries. I'm kind of curious to know how deep those boundaries go, and if there's any correlation between the one that seems to be going at greater depth and maybe their slip rate or whatever we might know.
Yeah, my first caution would be to say, once we start cutting horizontal sections through the moho, things get really messy, because I could be, the variation across the MOHO could be so much that we're looking at, whether or not you're above or below in the mantle or not. But this is saying, slow velocities deep down. So would that be, that maybe we haven't even hit the MOHO under the Brooks range? I haven't been a part of these studies to answer, but I would not, I wouldn't even jump to say that this is a Denali fault suture boundary. This could be just like I mean, what's really slow off here in the collision zone, and which was amazingly imaged by the PMP reflections off this active source experiment, was that the MOHO is like 55 kilometers down under southeastern Alaska at the deepest. As you go onto shore, it like drops down. So as you know, there's a great, Laurent is part of a paper by 2010 by Ron Ney and Jeff Abers looking at why this collision is shutting off volcanism in a place like Denali, where you might expect there to be a volcano, why you don't have it. So I don't know whether the images have elucidated the details, but partly why I'm excited is that none of these studies have used local earthquakes. So while I seem very late in the game maybe on using EarthScope data, I do hope that the kind of excitation of the crust and the high frequency wave field may be able to improve on some of these images. So I'm hoping that at least for that crustal scale correction question, we will get some better information. But I would expect there over the next time that someone will be doing some more detailed studies about the continuity of these structures. I know Sarah Ruskey would be an example of a geologist who's very interested to kind of link the gap between the surface and the geodynamics like you're working on.
Thanks, Laurent. So we have a question now from Mike.
It's a much more general question, but so this is amazing observations, both in spatial extent and quality from EarthScope. But you also mentioned there's lots of outstanding questions. If you could have additional measurements anywhere you wanted in this domain, where would you put them, and what question would you be asking of the data?
Boy, that's like a comps question.
Sorry.
I'm so far behind using the available data that I don't even think about that question, because I had two projects that were so draining and logistically challenging, and they were in Cook Inlet Basin. And I basically, after I'll give you two examples. Cook Inlet Basin, we put out stations by helicopter, by ocean boat. We broke boat propellers, their tides. It was crazy. But that was the place where I wanted to put stations more than anywhere. The other one was in Minto Flats, which is down a river. And I did that. And then we put out 400 stations, nodes along the Parks Highway for a 1-month deployment. So for me, that was kind of not my leading, I guess, but I was the logistical lead. I guess I would say I've covered the two places that I'm most excited about, and I haven't exploited the data. So if I show on this map, since we're here, I guess my targets, I'd be interested in, something more detailed. This is the Yukon Flats Basin along the, Denali-Tintina fault system. This is the Copper River Basin. And for me, if my overarching goal is to capture the kind of regional seismic wave field in Alaska, I would probably need more information about these. So there's oil and gas up here, but it's not very public, the information that comes out of that. And so kind of building up the shallow structure, I'd be interested to see, a little more information to get these shallower features.
And away from the active margin. Okay, great, thanks.
Yeah, thanks.
Well, I don't see any more raised hands, so I think we can open the floor back up to Ved and Wong-Han if they have questions. Yeah.
Sure. Can I go first?
Go for it, Ved.
So at the beginning of the talk, you were showing us an event up here in the northwest of Alaska, and you showed this beautiful coverage of the focal sphere by the stations.
Yeah. I'll get there.
I'm just going like chronologically. Yeah, there. So I guess didn't you maybe the previous slide showed some waveform fits, or the following slide? There we go. Okay, so for these kinds of things, I mean, when I look at those maps, the tomographic maps you showed, there's so much variability, so much 3D structure from shallow to deep everywhere, and some of it is so abrupt. When you do these things, can you get away with just using 1D velocity profiles, or?
I think so.
Yeah.
The reason is that so it may be that the one I'm showing here. So if you look at this and you think this is good, I see things that bother me. Like
No. Yeah, I mean, I'm
but-
looking at the things that bother me. Yeah.
yeah. So in this particular event, you my suspicion is that it's a source. There is a local structure issue. Like we have the data quality. If you can't fit the waveform, what are you left to explain? It's either the structure you're assuming or the source model. But for the most part, like the reason that these regional moment tensors are reliable enough, like this is a 16 to 40 second bandpass, and 16 to 40 seconds in my view is pretty long period, and a lot of the structure that's being shown in detail are smaller than that. And the body waves, although it's short period, like 1.5 to 3 seconds, they're often avoiding a lot of that structure. They're diving down and getting fairly clean waveforms. So we've done where I'm set up to do moment tensor inversions with 3D models. There you're limited by the quality of the 3D model. So if someone says this is the 3D model, I have handed you the Earth structure, I would be embracing that. But I know that there's this back and forth. I mean, for example, you're not going to have the right structure I need unless you used these kind of regional earthquakes. So if you use an ambient noise model down to sort of 8-second period, it may be some structure, but then it's an iterative thing. So as you know, like I do 3D wave field simulations, but in the realm of getting reliable sources, I much more gravitate toward trying to do the best data covered events first, rather than saying, I'm going to take this poor data coverage and use every sophisticated technique I have, because there are a lot of uncertainties in these beach balls. And if you look, this is really in the weeds here, but if you see the crossing near the nodal plane, near the nodal line. So for a seismologist, at that point, in that direction, if you're a station, you have no radiation. So when you're very close to there, there's extreme sensitivity to this mechanism by covering that crossing. So in this case, small changes in this mechanism will be picked up by big changes in the waveform. So that gives you an idea of why it matters to have, you can point at individual stations and get an idea of what would happen if you remove them. So the short answer is yes, we need 3D structure, but I think that the improved data here gives you a little more latitude to get away with things.
Do you have like different 1D profiles for different parts of Alaska?
Yeah.
Okay.
Yeah.
Because that works really well in California, so I don't see why it wouldn't work. And
you can see here, this shows the time shifts off of the surface waves. So you can see the fact that things are kind of green and yellow. In fact, this is another reminder, look how big they are. So this shows that with the 1D model, there's an 8-second time shift. Now, if you put in someone's 3-dimensional model in the long run, these colors should all collapse to what? Orange. Orange here is good, and yellow and green are bad. But you get an idea of, at least with respect to a 1D model, there's very large time shifts for considering these couple 100-kilometer paths. But the fact is that they're somewhat coherent, meaning that everything needs to be changed.
And when you do these, you do shift your synthetics with respect to the data, right?
Yeah, that's what these shifts. So 0.71 seconds, 4.25 seconds, and the body waves would be like a half second. So we don't, that's where the structure gets kind of wiped out, is just allowing time shifts. And so if this map looks all over the place and scattered, incoherent, then you've got a major problem with cycle skipping.
Yeah.
So, you know, in seismic imaging and in the oil industry, cycle skipping is this huge headache. It's also a headache in these studies, because when we go to shorter periods, it's difficult to see what cycles to align.
Okay. I actually have a bunch of follow-up questions on that, but maybe Monghan can ask some of it. Or maybe we can let people go so they don't listen.
Well, I didn't say I have more questions.
I thought you had 3.
Oh, it's exact. Well, if no one's asking a question, I actually have a pretty practical question. So I'm part of the subduction zone for the working group. And then last Saturday, we had a 3-hour-long debate about which subduction zone is better than the other. And of course, Alaska was on the table. So if you were asked that question, how would you advertise or sell Alaska?
Are we talking about U.S. taxpayer funded research, or just in general?
Just in general, like what is unique about Alaskan subduction zone?
Well, I think that there's a couple, you know, the man, where to begin with that? I would say first you have a shallow flat subduction, meaning the slab extends very far interior. Okay, like where I am in the center of the state here. Let me go up here. See if I have a better slab. I'm afraid I'm not going to find what I want, but I'm right here. Okay, the subducting slab is right below me. Okay, the extent of the slab. The slab is also extremely seismically active, so there's tons of information coming out. You know, Alaska versus Cascadia, there's no comparison. There's like probably 100 to, I don't know, 500 or 1,000 times more earthquakes in the slab. There's other cool things in Cascadia for sure, but you have a lot of activity in the slab to use information from. Then you also have this picture, which is the whole thing is deforming. There's discoveries to be made because no one can get out to these places, you know, and you know, 0 to 1 millimeter per year, no big deal, right? Okay, but there's magnitude 6 earthquake out near the oil field. There's a 7.3 earthquake out here. It's a big region to have this slip rate. And so you can have, it's like in Italy, you know, slow slip rates, but any given town can have a magnitude 6 every 1,000 years. So I think there's, and then when you look at the sort of slip budget of the subduction interface, you have, you know, you have non-volcanic tremor out in this region, showing you that the slab's actually extending to the east. You have slow slip events on this very deep portions of the slab in here, and then you have a locked megathrust that produces magnitude 9 earthquakes. So on the setting from sort of normal subduction to like Himalayan style collision right here, which are the highest, as I said, the highest coastal mountains in the world, and to your sort of standard strike slip fault system, which is something like 46 millimeters per year. It's considerably higher than the San Andreas Fault. You've got a lot, you know, a lot going on in this picture. So I don't know. I'm totally biased, as you can see.
I think I'm going to be biased as well now. You convinced me so well.
Yeah, thanks. Thanks, Monghan. I think that's a great question to end the main talk on. And then I believe Carl is available for discussion with the hardcore seismologists for a few more minutes. Is that okay, Carl?
Definitely.
Wonderful. Okay, but let's give Carl a big hand.
Hey, I really appreciate it. It's a really impressive turnout. You guys should be proud to be turning that many people out for these talks.
Thank you. Thanks.